In this video, we will be discussing Rademacher functions. The kth level Rademacher function is denoted by R sub k of t. These functions were first introduced by Hans Rademacher on 1922, and he showed that if a series, say En, is square summable, then the series Rn of t is also summable for almost every t on 0, 1. That is, you can say that if sigma n squared is finite, then sigma Rn of t is also finite almost every t on 0, 1. Right? So, here Rnt is the kth level of the Rademacher function, nth level of the Rademacher function. And these Rademacher functions will play an important role in the fields of the functional analysis and probability. In this video, I will discuss that the definition of the Rademacher function, the basic properties of itself, and some applications. Let's start with defining the kth level of the Rademacher function. We define R sub k on 0, 1 onto the set -1, +1 by R sub k of t equals to sine 2 k pi t for k in natural numbers. For example, if we graphically represented the first few Rademacher functions, you will see that in the first Rademacher function, the unit interval is being divided into two sub-intervals from 0 to 1/2 and 1/2 to 1. And in 0 to 1/2, the function value will be +1. And from 1/2 to 1, the function value will be -1. Similarly, in R2, we divide into 4 subsections, and the first one will be 1. In the second interval, the function value will be -1. And again, when you go to third interval, the function will flip back to 1. And in the fourth one, function will flip back to -1. So 1 and -1 alternates. Again, in R3, there will be 8 sub-intervals, and we can draw like this. So if I draw the kth level of the Rademacher function, there will be half of the intervals which have the function value of +1 and which have the function value of -1 as well. So you can define the kth level Rademacher function as +1 if t belongs to that upper half of the intervals, and rkt equals -1 if t belongs to the lower part of those intervals. And keep in mind that the Rademacher functions are connected with Lebesgue measure, so that we may omit countably many points. It does not change any of our results, so that I don't really care about the values at the ending points. Next, we will discuss some basic properties of the Rademacher functions. First one, integrating from 0 to 1, kth Rademacher function equal to 0. It's clear. If we go back to our graphical representations, you will see that in R sub 1, I am looking for the Lebesgue measure. So during 0 to 1 half, the Lebesgue measure will be 1 half. During half to 1, the measure will be negative 1 half. What do we see? Those are cancelling so that the integral value is 0. Similarly, in here we get 1 over 4, negative 1 over 4, positive 1 over 4, negative 1 over 4. Again, each of these are cancelling so that we get a 0. Like that, if I consider the kth Rademacher function, we will see that half of the intervals will have 1 over 2 to the k measure and the other half will have negative 1 over 2 to the k. So that each of these are cancelling and we will end up with having a 0. Therefore, integral 0 to 1 r sub k of t equals to 0. Next one. When you integrate the square function, you get 1. It's again clear because the square function will be strict at 1 because if rk is alternating between 1 and negative 1, square will be just positive 1. So that its integral is going to be 1. Alright. Next important property. If we multiply any n number of Rademacher functions and then find the integral of that from 0 to 1, that will be 0. So in this case, I will assume that without loss of generality, k1 is less than k2, k2 is less than k3, like that. K is the largest number. So I have written down the proof in the paper. Also, in this talk, I will discuss how to prove this for 2. But for the n cases, it will be exactly same idea, but the notations will be a little different. Alright, let's start. Suppose I want to find integral from 0 to 1 r sub s times r sub u dt dt, where s is less than u. That's the important fact. Now, I will first draw the function for the S level, or I will draw the S level Rademacher function. We know that in the S level, I divide the unit interval into 1 over 2 to the S sub intervals. So that I will have 1 over 2 to the S, 2 over 2 to the S, all the way up to, if I write down general term, I will have j over 2 to the s and j plus 1 over 2 to the s and all the way up to 1. That's the behavior. And since u is greater than s, we will note that 1 over 2 to the u is less than 1 over 2 to the s. Since u is greater than s. Therefore, in each of these intervals, there will be another 2 raised to the power of u minus s number of intervals in here. Say I can write this as, I will write this as, this length will be 1 over 2 to the u, like that. There will be, say, in each interval, there are, say, 2 raised to the power of u minus s number of intervals. So I can say some intervals with length 1 over 2 to the u. So if I draw that in the next plane, so I'm going to extract this picture j over 2 to the s to j plus 1 over 2 to the s. So in between this region, now I will have a couple of more. So j over 2 to the s plus 1 over 2 to the u. Next one will be j over 2 to the s plus 2 over 2 to the u. Like that we will continue. And keep in mind that in between j to j plus 1, the function r sub s will be either positive 1 or else negative 1. It will remaining at a constant value. So that when I am finding integral 0 to 1, I want to find integral 0 to 1 r sub s r sub u dt. So instead I will first find, this is what we need. Let's first find the integral from j over 2 to the s to j plus 1 over 2 to the s r sub s r sub u dt. We know that rs is a constant value in between this interval, so that I can say it's a c. C is either negative 1 or positive 1, and I will take that out. What can we say about the integral between this region for r sub u function? We know that the r sub u function will be alternating like this, and there will be exactly even number of intervals with a positive value, positive measure, and there will be exactly another half of the intervals with the negative measure, and again they are cancelling, so that we get this to become 0, which ended up with having a 0. This is for j to j plus 1, but we know from 0 to 1 rs ru dt equals to sigma, say j running from 0 to 2 to the s minus 1 integral j over 2 to the s to j plus 1 over 2 to the s, rs ru dt, and we know this value is particularly 0, so again when I sum up any more numbers with zeros, it will be still 0. Third one, we want to find this one. Okay, let's start. So in order to find this, I will keep the integral sign as it is first. I am going to break this apart. So we will see that we can get the squares of each of these. So I can write this as I running from 1 to n r sub ki square and t, right? And plus we will multiply each of these. So we have, say, I and j, I less than j. So we get rki, rkj, and we get twice of these guys. And then we know that, okay, now I can split the integral into both of these sections, and since each of these are finite sums, I can take them out. So I will say 1 to n, 0 to 1 rki square t plus sigma 2 times sigma integral rki rkj. And what do we see? The second term is exactly 0, because from part 2 we know this integral is 0, so summation is still 0. And from part 1 we know this is equals to 1. So I am looking for sigma running from 1 to n of 1, which is exactly n. Next, we will discuss some applications of the Rademacher functions in functional analysis and probability theory. We will start with probability theory. In probability theory, we use the law of large numbers to study the asymptotic behavior of the random variables. Suppose we have x1, x2 up to xn random variables which are independent and identically distributed with mean 0, and then the law of large numbers says that average of these n number of random variables tends to 0 as n tends to infinity. In particular, we are interested in the weak law of large numbers. The weak stands for whenever the convergence is in measure, we say it's a weak convergence. So, we feel particularly interested in weak law of large numbers. And in our setting, we will replace the random variables by the Rademacher functions. And we can do that because we know for the random variables, we have a criteria as independent. Yes, it is same for the Rademacher functions also, because we know that the integral of the product of the Rademacher functions are equal to 0. So they are orthogonal. So I can take them as independent. And similarly, I can take that to be Rademacher functions are to be equal to 0. The mean of these are equal to be 0, since the Rademacher functions integral is also 0. So then we will replace the random variables with the Rademacher functions. So let's take this theorem. Let mu to be the uniform probability measure on 0, 1. Then for each epsilon greater than 0, the limit of the mu of this set is greater than epsilon is equal to 0. We will prove this theorem using the help of the Rademacher functions. So, and these are Rademacher functions. Let's prove that. So we will just write it easily. I will denote the set of all T such that the property holds as A sub n. Now, using Chebyshev, we can say that measure of an is less than or equals to 1 over n squared epsilon squared integral over A sub n rk1 of t plus rk2 of t all the way up to rk sub n of t perfect square dt. And we know that this is less than or equals to 1 over n squared epsilon squared 0 to 1. Since n is a subset of 0 to 1, I can do that. So 0 to 1 r k1 of t all the way up to rkn of t perfect square dt. And we know that from our property 3, this is equals to n. So I can say this is equals to n. So we have this times n. Therefore, we ultimately get 1 over n epsilon. Now, once you take the limit, you will see that this is equal to 0. This completes our proof. All right. Next application. A complete orthonormal basis for L2. The idea is we will use the Rademacher functions with the help of the Walsh functions to obtain a complete orthonormal basis for L2. First note that the collection of all Rademacher functions will not create a complete orthonormal basis for L2. To see this, we can consider R1 times R2 and let big R be the span of Rademacher functions. Then for each R in R is orthogonal to R1 times R2. We can show this using the properties that we discussed. And the limits norm of the limit R1, R2 minus R is greater than or equals to the norm of R1, R2, which is equals to 1. So that this is not going to be a complete orthonormal basis. In order to make this complete, we define new set of functions namely Walsh functions. This is how we define omega naught equals 1 and omega sub k1, k2 all the way up to kn equals to rk1 times rk2 all the way up to rkn for k1 less than k2 less than kn. And since any continuous function can be approximated by the Walsh functions and continuous functions are dense in L2, therefore we can say that this new system will create a complete orthonormal basis for L2. In my paper, I have included another example from the functional analysis. It's regarding the averaging Barnum spaces. If you are further interested, you can have a look on it also. So that's all about it. Thank you so much.